Hi all, we're going to have a session on combinatorics, on permutation and combination. So as always, the questions will be posted on YouTube live chat. You'll also be able to see this on our Facebook events page. So have a go at the questions. We're going to do this practically as one long session. We have about 12 to 13 questions here. Nice. We've tried to pick questions at the right level of difficulty. So we're saying CAT plus 15-20% level of difficulty, minus 10% level of difficulty. We're not going for very easy questions, but none of these questions is outlandishly tough. So if you're saying you're ready for this topic, out of these 12, 13, you should be able to attempt and have a go at 9 to 10. That's what you're looking at. We're getting close to the exam, so there's no point saying that this is a buffer and we're starting at step 0 and all that. And now from now on, you should become game ready. And so that is the idea behind this class as well. Questions are not easy, but are not outlandishly tough. You should be able to solve these. And so, as ever, if you have any questions, queries, doubts, post them on the panel. One of my colleagues who's moderating the session will be able to answer those. I'm going to slip into screen share mode because we are solving and simplifying, seeing the question and seeing the description, seeing the discussion. That makes way more sense. I'm going to share the screen and then run over to answering each of those. Question number 1, I'm going to give you only about a couple of minutes to think about it, all over it, to give it a go, and then I'm going to discuss this. How many 6-digit numbers exist comprising only the digits 2 and 4, such that they are multiples of 12? Remember, the number should have 6 digits. The only allowed digits are 2 and 4. The number should be a multiple of 12. Okay. 3 conditions: 6-digit number, should have only 2s and 4s. The number should be a multiple of 12. I'm going to have a go at cracking this. Think about this: 6-digit number, 1, 2, 3, 4, 5, 6. So looking at numbers like 2, 2, 4, 2, 4, 2, 2, 2, 4, 2, 4, 4. I'm not saying these numbers satisfy the condition. They may or may not. 6-digit numbers with only 2s and 4s. The number should be a multiple of 12. So think about what needs to go in and what will be the order in which we approach this. So lots of times I find students going through sets of possibilities without narrowing down and hitting the best one to start with. And here the best one to start with is this condition. Wonderful condition. The number should be a multiple of 12. That means it should be a multiple of 3 and a multiple of 4. Multiple of 4, the last 2 digits should be a multiple of 4. Multiple of 3, sum of all digits should be a multiple of 3. Then you are dealing with only 2s and 4s. The last 2 digits can be 2 and 2, 2, 4, 4, 2, or 4, 4. We want the last 2 digits to be a multiple of 4. This is out, this is out. So you can straight away say our number should either end in 24 or should end in 44. One of these two. Now let's go to the other condition, which says that the number should be a multiple of 3. For a number to be a multiple of 3, sum of all the digits should be a multiple of 3. The best way to go about these questions is to think about the smallest possible sum, largest possible sum, work our way in between. The smallest possible sum, all digits are 2. So sum of all digits is 12. Largest possible sum, all digits are 4. 6 fours, sum of all digits is 24. So the sum of all digits can be between 12 and 24. If you have 6 2s, you get this. If you have 6 4s, you get this. What else is possible? You could have 5 2s and 1 4. You could have 4 2s and 2 4s. You could have 3 2s and 3 4s. 2 2s and 4 4s. 1 2 and 5 4s. These are the combinations possible as far as we're thinking about how many 2s are there and how many 4s are there. And sum of all these digits is 12. These are 5 2s and 1 4. 10 plus 4, 14. 4 2s and 2 4s. 4 into 2, 8. 2 into 4, 8. Total 16. 3 2s, 6 and 3 4s. 12, 18. This will be 20. This will be 22. If you think about it, from one sequence to the next, we are removing a 2 and adding a 4. The total will go up by 2. Which of these are multiples of 3? This will work. This will work. This will work. So we could have all 6 2s, we could have all 6 4s, or we could have a scenario where there are 3 2s and 3 4s. All 6 2s is not possible, because if all 6 were 2s, then the number would end in 22 and therefore not be a multiple of 4. So that's ruled out. All 6 4s, that's a possibility. All 6 4s is one number, wonderful number. 4 4 4, 4 4 4. That's a multiple of 3 and a 4. It's already in. So we could have one number which is 4 4 4 4. Now 3 2s and 3 4s. That's the one we are looking at. That will probably have more combinations. Now our number could end in 24, or it could end in 44. If it ends in 24, before this, the first 4 digits should be 2 4s and 2 2s. If it ends in 44, the first 4 digits should be 3 2s and a 4. These can be rearranged in 4 factorial by 2 factorial into 2 factorial ways. These can be rearranged in 4 factorial by 3 factorial ways. This is 6. This is 4. So 6 numbers of this type, 4 numbers of this type, and this one number, which is 4 4 4 4 4 4. Or we are looking at 6 plus 4 plus 1, 11 possible numbers. Okay. You get a lot of questions on combinatoric permutation combination, which is a combination of number systems and counting. And here you're using the idea that a number that's a multiple of 12 is a multiple of 3 and of 4. 3, sum of the digits, 4, last 2 digits. Isolate the last 2 digits, then worry about the sum of the digits. Sum of the digits should be a multiple of 3, try different combos. Only 1 or 2 work. Within that, incorporate this condition of last 2 digits and then simplify. So, very doable question. If you do a couple of questions of this template, your speed will shoot up. You can do these questions much quicker. But even otherwise, very simple question, very doable question. I won't say it's a simple question, but doable in that 2.5 minute time mark that you're looking at. I'm going to go to the next one. Have a go at this. Again, it's a good question. I'm going to pause for maybe a minute, minute and a half before I start talking about how to solve this. So keep trying this. The 4-digit numbers should have a product of their digits equal to 48. And all of these combinatoric questions, there's got to be kind of a method to which the way you count. That is very vital to get the right sequence, the right order in which you're going after the constraints given in the question. These questions look very simple. If you're going about them in the wrong order, but you can list down all 4-digit numbers and then simplify that, then it's a nightmare. And the product of the digit should be 48. So you've got to say product is 48. Let me think of a number, and then let me think of a pattern to finding this. So pattern to counting this so that I end up counting all the numbers. I shouldn't miss out on anything. There are 49 possibilities totally. Nobody is going to give you any mark for listing 47 of them. So you've got to get everything. So that rigor is very important. Actually, your method has to incorporate that. I'm going to think about some number and then start from there. Product of the numbers is 48. So I could have say 1 into 3 into 4 into 4. 1 into 3, 3 into 4, 12, 12 into 4, 48. This works. Okay. But I keep writing numbers like this and going nowhere. I found a 1. Okay. So I'm going to break this question and say, look, there is a 1 sitting there. There are 4-digit number. Let's say the 4 digits are A, B, C, D. I'm going to say A less than or equal to B less than or equal to C less than or equal to. So I have a hierarchy here. I have a method to the way I count. Obviously, once I find the number, I'll find all the arrangements of that number. If I have 1, 3, 4, 4, I can obviously have 3, 4, 1, 4. So now, the smallest digit I can have is 1. I want to see how many ones I can accommodate, maximum. Let's say I can accommodate 1 1, that is possible. Can I accommodate 3 ones? 1, 1, 1 and something, the product won't be 48. Is it possible to accommodate 2 ones? Can I have 2 ones in the system? So that means I'm looking at a number which is the form 1 1 xy in some order. So x into y is 48. So it cannot be 24 into 2 or 12 into 4. It's a single digit numbers, but it could be 6 into 8. So I've got already a winner, 1168. After done that now, I like 1168. I've got something there. With 2 digits being 1, this is the only combination. So now I'm going to say, with 2 digits being 1, I've got only one combination. I'm going to have one of the digits as 1. And then I know these three are not 1, they're greater than 1. Let me put this as 2. Now 1, 2, xy product is 48. Our x into y should be 24. So if you're looking at two single digit numbers multiplied to give 24. So x into y could be 3 into 8, it could be 4 into 6. 2 into 12, 1 into 24, those are rolled out. So we have two more. We have 1, 2, 3, 8, 1, 2, 4, 6. And so starting with 1, 2, we've got that. Can we do better than that? Are there more combinations with 1, 2 available? With 1, 2, then the remaining product is 24, only 2 combinations available. Now, can we go for 1, 3, xy? With these two multiplied to give 16. So two single digit numbers multiplied to give 16. It could be 4 into 4. It could be 2 into 8. But remember, I shouldn't count 2 into 8 because I could have already accounted for that 2 here. I have A less than or equal to B less than or equal to C less than or equal to 2. If I count 1, 3, 2, 8, that means I'm double counting this 1, 2, 3, 8. So if I have 1, 3, these two numbers should be 3 or more. Only possibility is 1, 3, 4. Now let's go to numbers starting with 2 because 1, 4 and then beyond that 1, 4, 4, 4 the product is 64. That's not possible. With 1, 3, 4, 4 we fit the best case scenarios with 1 in the mix. So let's put 2 in the mix. Let's say we'll put 2 here and a 2 here. Because the second digit cannot be 1. It has to be at least 2. So the smallest possibility 2, 2. We have 2, 2, xy. X into y in this scenario is 12. 12 can be written as 2 into 6, 3 into 4. 1 into 12 of course will rule out. Both of these are possible because 2, 2, 2, 6 remains a possibility. 2, 2, 3, 4 remains a possibility. Right? So with 2, 2, only these are possible. Let's go to 2, 3. 2 into 3 is 6. So x into y should be 8. This should be at least 3. This should be at least 3. 3 into 3 is 9. So this is just not possible. It's never going to happen anything like this. So our digits could be 1, 1, 6, 8, 1, 2, 3, 8, 1, 2, 4, 6, 1, 3, 4, 4, triple 2, 6, double 2, 3, 4. And how many ways can this be done? This is 4 factorial by 2 factorial. This can be done in 4 factorial ways. This can be done in 4 factorial ways. 4 factorial by 2 factorial. 4 factorial by 3 factorial. 4 factorial by 2 factorial. So it's 12 ways can be rearranged. 24, 24, 12, 4, 12. Add all of this up, got your answer. 12 plus 24, 36, plus 24, 60, 72, 76, 88. And I did this question the first time around, I missed one number, one combination, and I got the answer as 84. So, very good question, very doable question, kind of question where you can slip up. In all of these questions, it's very easy to get a few numbers. It's very easy to get some kind of algorithm to check. But it's very important to count with the pattern. This pattern right here, one of them. Remember, I'm not saying the 1000th place should be less than or equal to the 100th place, less than or equal to 10. I'm saying there are 4 digits in this number. I'm going to call them A, B, C, and D. I'm going to count with the pattern that A less than or equal to B less than or equal to C less than or equal to D. I'm going to think in terms of what are the smallest values A, B, C can take. So I'll start with assuming that they're all 1. Then that doesn't work. Some are 1. And slowly crank up. This way I know I'm not missing anything. So this algorithm of counting, this mechanic of counting, where we say that keep some pattern so that you don't miss out anything. If you missed out this number or this number, you're going to be out of whack. Your answer is going to be off by a margin. But combinatorics is very much about getting stuff right and making sure that you have a method to ensure that nothing goes wrong. That is vital. So keep an eye open for that. Now go to the next question. This is more a plain vanilla regular question. Give it a go. In how many ways can we rearrange the letters of the word aptitude such that no two vowels are next to each other? How many ways can we rearrange the letters of the word aptitude such that no two vowels are next to each other? Tricky question until you get to know the idea. Once you know the funda, is a very mechanical, routine question. So, what are the vowels in this word? We have A, I, U, E. This word has 1, 2, 3, 4, 5, 6, 7, 8. The consonants are P, T, T, D, and the vowels are A, I, U, E. So no two vowels should be next to each other. Right? The method for these kind of questions is very standardized. Don't count overall number and subtract combinations where two vowels are together, three vowels are together. You'll never be able to find out where the double counting is happening. The method is very simple. Put the four consonants first. How many ways can these be arranged? 4 factorial by 2 factorial, which is 12 ways. Once you put the four consonants in place, some order, introduce a seat between any two consonants. Remember, it is only one slot between any two consonants. Introduce one right at the beginning, right at the end. There are 5 slots now created between the consonants, one in the beginning, one at the end. Now, if the 4 vowels were to occupy any 4 of these 5 slots, then our condition would be satisfied. Our condition is that no two vowels be next to each other. If I put an A here, I here, U here, E here, that will work. Put A, I, E and U here, that will work. And I'll account for all the possibilities where this happens. So out of these 5 slots, 4 have to be taken up by vowels. How do we do that? By C4. Now we say this, and this are taken up by vowels. So A, I, U, E have to go in there. In how many ways can we have A, I, U, E sitting there? 4 factorial ways. So we have 4 factorial by 2 factorial ways into 5C4 into 4 factorial for arranging the consonants, for selecting the slots, for arranging the vowels. 12 into 5 into 24. Or 60 into 24, 1420. So not bleeding obvious question, but regular fare as far as this exam is concerned. No two vowels need to be next to each other. No two boys should stand next to each other. The treasurers should never be near each other. So secretaries should at least have one person in between any two secretaries. All of those follow the same pattern. Here, no two vowels should be next to each other. Put the consonants first. Rearrange them in as many ways as possible. Create slots in between. Select slots for vowels. Then plug in vowels and rearrange it as many ways as possible. Go to the next question. Years ago, I'm just going to flip out of screen sharing, have a quick look at the YouTube chat interface, and then come back to screen sharing. So I hope you're all able to solve this, able to clearly see this. I'm going to jump to the live event interface just to see the chat, and then we'll discuss how this goes. So keep trying that question. I'm going to see this. There isn't much to be worried of here. So I don't think there are too many questions here that we need to worry about. I'm just checking the chat window on YouTube. So there seems to be nothing funny going on there. I think you can all hear me clearly on the rest of it. I'm just worried about how many conditions would be there. So it's just that there's something chaotic there. So that is done. So I'm going to go revert to the screen sharing option and then solve the subsequent question. So we'll share this. A die is rolled thrice. What is the probability that the product of the three rolls is greater than 100? Once again, a wonderful question because it's a fun question to solve. Think about. A die is rolled thrice. What are the total number of outcomes? I always love finding the total number of outcomes because that just puts in place our denominator. Denominator is 216. Why so? 6 cubed. 6 into 6 into 6. 6 outcomes for the first row, 6 for the second one, 6 for the third one, 6 cubed, 216. Total possibilities is 216. Right. Now, we have A, B, C. The product should be greater than 100. I'm not going to think of this as A in the first row, B in the second row, C in the third row. These are the outcomes in the three rows. I'm going to say A less than or equal to B less than or equal to C. Why this? So that there is a pattern to our counting. And there are three rows. The smallest one were 1. And the product of the remaining 2 should be 100 or more. That's not possible. The smallest one were 2. Product of the remaining 2 should be 50 or more. That's not possible either. The smallest one were 3. Product of the remaining 2 should be 33 or more. That is possible. So therefore, the smallest of the three rows cannot be less than 3. It should be 3 or more. And now I've got a pattern. So I'm going to start with 3. Then B and C are 3 or more. That much I know. So I don't really have to worry about 1 and 2. None of my outcomes is 1 or 2. So I'm already dealing with only 3, 4, 5, 6. So 3 into 3 is 9. 9 into something won't work. 3 into 4 is 12. 12 into anything won't work because we cannot get 100. So 3 and 3, 4 are out. 3 into 5 is 15. 15 into 6 is 90. Even that doesn't work. So 3, 5, 6 also doesn't work. 3, 6, 6. 3 into 6 into 6. 36 into 3 is more than 100. That could work. So starting with 3, the smallest of the 3 numbers being 3, 366 is the only possibility where the 3 numbers, the 3 digits multiply to give us more than 100. The smallest of the 3 throws, 3 outcomes were 3, and we have only one possible set of outcomes, which is 366. Now let's move to 4. 4, 4, 6. 4 into 4, 16. 16 into 6, 96. So 4, 4, 6 doesn't work. So starting with 4, 4, we don't have anything. So let's move to 4, 5. 4, 5, 5 is just 100. That doesn't work. 4, 5, 6 would work. 4, 4, 6 doesn't work. 4, 5, 6 would work. 4, 6, 6 will obviously work. So starting with 4, not saying the first row is 4. The smallest of the 3 throws is 4. So the total could be 4 into 5, 20 into 6, 120. So 4, 5, 6 is possible. 4, 6, 6 is possible. Now let's put the smallest throw as 5. So that could be 5, 5, 5, 5, 5, 6, 5, 6, 6. The only 3 possibilities. The smallest is 5. Could be all 5. Could be 5, 5, 6, 5, 6, 6. 5 into 5 into 5 is 125. This works. Obviously, these two will work. So all 3 are possible. 5, 5, 5, 5, 5, 6, 5, 6, 6. All of them are possible. Beyond this, we could have a scenario where the smallest is 6, which gets 6, 6, 6. That is obviously possible. Now let's come to the counting part. 3, 6, 6. In how many ways can this happen? It could be 3, 6, and 6. 6, 3, 6. 6, 6, 3. 3 ways. Or 3 factorial by 2 factorial. This you should know. A, B, B can be rearranged in 3 factorial by 2 factorial. That you should know. That's not negotiable. 4, 5, 6. This can be done in 6 ways. This is 3 factorial. 4, 6, 6. 3 ways. 3 factorial by 2 factorial. 5, 5, 5. Only 1 way. 5, 5, 6. 3 ways. 5, 6, 6. 3 ways. 6, 6, 6. 1 way. Once you crack the fund, I'm just doing this part mechanically. 3 plus 6, 9. 9 plus 3, 12. 12 plus 1, 13. 3, 16, 19, 20. 20, by 216, whatever that term will be. 10 by 108, 5 by 50. The product should be more than 100. So what are all the sequences or what are all the sets of numbers that can work? Find that out. So 366 can work. Then in how many variants can that happen? 366 could be 636, 663. 456 can happen in 6 different ways, 3 factorial. Count all of them, add all of them up. That's our numerator. Our denominator we've already discussed. 6 into 6 into 6, 216 done. So 20 by 216, whatever that is. Go to the next question. If a class has 5 students, what is the probability that no 2 are born on the same day of the week? A class has 5 students. What are the odds that no 2 are born on the same day of the week? I'm going to give you about 30 seconds, 45 seconds to have a go at this. 5 students, what is the probability that no 2 are born on the same day of the week? So they could be Monday, Tuesday, Wednesday, Thursday, Friday. Be some 5 out of the 7 days of the week. But there shouldn't be 2 born on the same Monday or 3 born on a Tuesday. That's not possible. The class has 5 students. Think about this, there are 5 students, say A, B, C, D, E. A could have been born on Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, any of the 7. B, any of the 7. C, any of the 7. D, any of the 7. E, any of the 7. There are 7 possibilities for each of these people. Are a wonderful denominator, the part which we love doing. The total number of possibilities is 7 or 5. Now let's move to the numerator. The first guy, A, could have been born in any of the 7 days. So 7. And then B could have been born in should have been born in one of the remaining 6 into 6. C has 5 options. D has 4. E has 3. Or 7 into 6 into 5 into 4 into 3 by 7 bar 5. Wonderful question, very simple question. 7 into 6 into 5 into 4 into 3 by 7 bar 5. Now, we're going to discuss one option here. Very often I find students saying 7 bar 5 here, 7C5 here. It should have been born in 5 different days of the week. It could have been Monday, Tuesday, Wednesday, Thursday, Friday, Sunday, Saturday, Monday, Tuesday, Wednesday. So which 5 are they born at? Out of 7 days, select 5, 7C5. This is wrong because now we don't know if the days of the week were Monday, Tuesday, Wednesday, Thursday, Friday. Who was born when? That is important. It could be like this or it could be like this. Now, it is important point. If you have slightest bit of doubt, do you need to account for both of these or not? Think about what your denominator is accounting for. My denominator will count this and this. In my denominator, I am accounting for both A, B, C, D, E being born Monday to Friday or B, A, D, E, C being born Monday to Friday. Since my denominator is accounting for both, my numerator should account for both as well. So this is not 7C5 by 7 bar 5. 7 into 6 into 5 into 4 into 3 by 7 bar 5. So remember that this is wrong. That is very vital. It is important to know what is the wrong answer. Why is that wrong? We'll go to the next question. How many scalene triangles with integer sides exist such that the product of 2 of the sides is 12? Again, wonderful question. Scalene triangles, integer sides, product is 12. 3 different constraints. You get wonderful combinatorics question where you dabble with 3 constraints and then there is a condition that is sitting there. Here the condition is sum of 2 sides of the triangle should be greater than the third side. Some of the 2 shorter sides has got to be longer than the longer side. I think that's very important. Some of the 2 shorter sides has to be more than the longer side. How many scalene triangles are there? All 3 sides should be distinct and should be integers. So multiple conditions, multiple constraints to work with, and that one condition we need to be worried about. Product should be 12. So 12 can be 1 into 12, 2 into 6, 3 into 4. So 2 of our sides could be 1 and 12, or 2 and 6, or 3 and 4. Now 1, 12, 1, 112 2, 112 3, 112 4, 112 5. They're all not possible triangles. Sum of two sides has got to be greater than the third. So 1, 12, 7. 1 plus 7 is 10, 12. It's not even a possible triangle. So 1 plus 12 should be greater than the third side. Sum of those two should be greater than 12. Think about this. What could be this third side? 1 plus 12 should be greater than k. 1 plus k should be greater than 12. So what are the possible values? Even if k were 11, 1 plus 11 is not greater than 12. If k were 13, 1 plus 12 is not greater than 13. The only possible value k can take is 12. So the two sides were 1 and 12. The third side has got to be 12 for us to have a possible triangle. But we know that the triangle we're looking for has to further be a scalene triangle. So this doesn't work. There's nothing possible with 1, 12. Now let's move to 2, 6. 2, 6, 1 doesn't work. 2, 6, 2 doesn't work. 2, 6, 3 doesn't work. 2, 6, 4 doesn't work. 2, 6, 5 will work. 2 plus 5 is greater than 6. 2, 6, 6 will work. 2, 6, 7 will work. 2 plus 6 is greater than 7. 2, 6, 8 won't work. So the sides of the triangle were 2 and 6, and the third side could be 2, 6, 5, 2, 6, 6, 2, 6, 7. 2, 6, 6 is isosceles. Forget about this. These two are possible. Now let's move to 3, 4. 3, 4, 1 won't work. 3, 4, 2 can work. 3, 4, 3 can work. 3, 4, 4 can work. 3, 4, 5 can work. 3, 4, 6 can work. 3, 4, 7 won't work. 3, 4, 1 does not work. So 3, 4, 1 won't work. 3, 4, 7 won't work. 3, 4, 2, 3, 4, 3, 3, 4, 4, 3, 4, 5, 3, 4, 6 will all work. Remember, we are looking to find scalene triangles. This we should count. This we won't count. This we won't count. This we should count. This we should count. Or we're looking for scalene triangles with integer sides where product of two sides is 12. We'll have 2, 6, 5, 2, 6, 7, 3, 4, 2, 3, 4, 5, 3, 4, 6. 5 different triangles. No rocket science here. Methodical counting, but counting with some rigor. 1 into 12, 2 into 6, 3 into 4. Nothing possible with 1 into 12. Only one triangle is positive, and that triangle is isosceles. 3 triangles with 2, 6. One of those is isosceles. Remaining 2 get counted. 5 triangles with 3, 4. 2 are isosceles. Remaining 3 get counted. Put them together, we have 5 possible triangles. About this, in how many ways can we select 3 cards from a pack of cards such that all 3 belong to different suits? Very good question, very simple question, the kind of question where you can write down the answer and compute and mark the choice in 45 seconds. But it's a good question because you can get stuff wrong. It's very important to think about which way we are approaching this. In how many ways can we select 3 cards from a pack of cards such that all 3 belong to different suits? All 3 should belong to different suits. The cards should be from 3 different suits. 4 suits: club, diamond, hearts, and spade. Out of these 4 suits, our card should belong to 3 suits. Be CDH, CDS, CHS, DHS. Out of 4, we have to select some 3 suits. 4C3. Now assume we've selected one. Out of this, out of this 4C3, we're saying our cards are from club, hearts, and spade. We've got 1 card from club, 1 from heart, 1 from spade. 1 from club is 13C1, 1 from heart, 13C1, 1 from spade, 13C1. Or this is 4C3, which is 4, 13Q. Done. So reading the question and writing down the answer. Now, what is the wrong way of doing this? So from a card pack, we're selecting 3 cards such that they should belong to different suits. The first card, there's no condition. 52 choices available. Once I've selected this first card, whatever suit we selected this from, we eliminate the entire suit. The first card were a club, we eliminate all clubs. So we have 39 cards remaining to 39. Second pick. The third pick, this suit also completely disappears into 26. This answer is wrong. Why is this wrong? You could have selected 3 club, 4 diamond, and 7 hearts. Or it has selected 7 hearts, 3 club, and 4 diamond. Both of these will get counted here. We should not be counting both. We should count only one of those. So there are 4 suits available, of which our cards are from 3 suits. So we need to pick from 3 suits out of 4, 4C3. Now that I've selected the suits, I go back to each suit and select 1 out of 13. 13C1, 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 4 into 13C1 whole cube, or 4 into 13 cube. Very simple question, you just mark the answer straight away. But don't break it into this weird step-by-step process where we say from 52 we select, from 39 we select, all that. Don't do that. So, wonderful question. I'm going to take one other break where you're just going back to the YouTube screen to see if there are some questions. Take a couple of minutes, have a go at this, then we'll come back. So I'm just having a look at the chat window. So again, it's a good question. So I'm going to give you a couple of more minutes to try to solve the question. So it's not too difficult. It's very doable. But take a minute and a half to try that question and see how it works, and then we'll discuss this. So I'm going to flip back to screen sharing at question number 8 or 9. We have about 18 questions totally, but 13 are the ones that I want to discuss. The remaining 5 are too tough, way too tough for CAT. Maybe one day we'll get together all these fun, wacky, tough questions which are impossibly tough and very extremely, extraordinarily unlikely to be in CAT, and then do it for the heck of it. But you're not wasting precious time before the exam proving that we can do great questions. That's not what we're about. We want to solve relevant questions, lots of them, and get the processes right. So I'm going to go back to screen sharing and then continue with what you're doing. Set A has all factors of 1080. Set B has all factors of 2800. How many elements are present in A union B? Again, 1 unit of number systems, 1 unit of combinatorics. Put together, you'll get lots of questions in that territory. Here you have 1 unit of set theory as well. Brilliant, the best of all 3 worlds. And set A has all factors of 1080. Let's start with that. 1080. Prime factor is 108 is 2 square into 3 cube. So we have 2 cube into 3 cube into 5. 10 is 2 into 5. Combining that. Should be extraordinarily comfortable with prime factorization. So get lots and lots and lots of practice to that. And so, how many factors does this number have? 3 plus 1 into 3 plus 1 into 1 plus 1, 4 into 4 into 2, 16 into 2, 32 factors. So A has 32 elements. It's going to be just 2800. Just 2 square into 7 into 2 square into 5 square. 2 power 4 into 5 square into 7. I'm just prime factorizing 2800. How many factors does this number have? 4 plus 1 into 2 plus 1 into 1 plus 1. 5 into 3, 15 into 2, 30. So set A has 32 elements, set B has 30 elements. We need to find how many are present in A union B. 32 plus 30 is 62. Right? A has 32, B has 30. So totally they should have 62. Is that right? Is that right? There's something funny that's going on here. There will be quite a few elements that are present in both of these sets. Number 1 will be there in both these sets. 2 will be there. Both are multiples of 4. Both look to be multiples of 10. So there are some elements that are present in both of them. If so, we need to find how many elements are there in A union B. We know how many are there in A, how many are there in B. We subtract how many are there in A intersection B. We are good. The number of elements in A union B, number of elements in A plus number of elements in B minus number of elements in A intersection B. So if we do this, we are good. We know this, we know this. We need to get a handle on this. We want to find how many elements are present in set A and set B, or how many numbers are factors of 1080 and 2800? Or how many of these are common factors of both these numbers? How do you find how many common factors are there? Find the HCF. If you find the HCF, then all factors of the HCF are factors of both these numbers. Done. What is the HCF of these two numbers? 2Q into 5 power 1. No 3, no 7. No 3 in this number, no 7 in this number. So the HCF is 2Q into 5 power 1. So the number of factors of this number is 3 plus 1 into 1 plus 1. 4 into 2, 8. So set A has 32 elements. Set B has 30. A intersection B has 8. So A union B will have 32 plus 30 minus 8. 32 plus 22, 54 elements. A union B will have 54 elements. Very good question, doable question, simple question. Just using 1 unit of set theory, 1 unit of number theory, 1 unit of simple counting, finding number of factors. Next one. How many integral factors of 720 are not factors of 2310? How many integral factors of 720 are not factors of 2310? I don't know how to go over this. So I'm going to do a trick one. 720 is 2 square, 2 cube into 3 square, that is 72, into 10. 2 power 4 into 3 square into 5 power 4. 2310. This is 231 into 10. 231 is multiple of 3. So 3 into 77 into 2 into 5. Now this number is 2 into 3 into 5 into 7 into 11. Oh, quite an interesting number. The sum of the product of the first 5 prime numbers. I don't know how to do this question, and so I'm just starting off by saying, let me prime factorize this. Let me prime factorize this. So now I want to find how many integral factors of 720 are there that are not factors of this number. So if I find factors of 720, and then I say I'll knock off the common factors, I should be good. Let's find how many factors are there for 720. You should know this formula, you should know why this formula works. It's 4 plus 1 into 2 plus 1 into 1 plus 1. 5 into 3 into 2, so it's 30. Our answer is less than 30. 720 has only 30 factors. From this, we are going to remove numbers that are factors of 2310 also. We're going to remove numbers that are factors of 720 and 2310. We're going to remove all common factors. Our 2310 is this number. 720 is 2 power 4 into 3 square into 5. Again, find the HCF. HCF is 2 into 3 into 5. All factors of this HCF will be factors of 720 and 2310. Therefore, if we remove all of them, we get what we are looking for. So HCF is this. Number of factors of HCF is 1 plus 1 into 1 plus 1 into 1 plus 1. Or there are 8 factors that are common to both of these. 720 has 30 factors, of which 8 are also factors of 2310. 22 numbers are there that are factors of 720, but not factors of 2310. That's the answer we're looking for. That's a wonderful question, absolutely fabulous question, one of my favorite questions. Give it a go. I'm going to give you exactly 45 seconds to go for this, and then we'll discuss the answer. Okay, so one of my favorite questions, because it's one fabulous first principles based, rigorous, wonderful method. And then there's this, oh my god, this is so easy method. And so I'm going to do it by both methods. Fine, so give it, I'm going to give you like say 10, 15 more seconds, keep talking some gibberish till then, and then jump in, dive in and solve this question. 8 tosses a coin 11 times. What is the probability there will be more heads than tails? As always, denominator is 2 power 11. More heads than tails. It should be either 6 heads or 7 or 8 or 9 or 10 or 11. 5, 4, 3, 2, 1, 0. There will be more tails than heads. So this is 11C6 plus 11C7 plus 11C8. I don't want to do any of this. I don't want to do any of this. don't want to calculate 11C6, 11C7, 11C8, none of that. I don't want to do it by that. A tosses a coin 11 times. So what is the probability there will be more heads than tails? Think about this. What is more likely? There will be more heads than tails or more tails than heads? So these are equally likely. If you have H, T, T, etc., etc., if you flip it, you'll get the other possibility. So more heads than tails and more heads than tails are equally likely. Probability of H more than T equal to probability of T more than H. Any scenario this is true. What is the probability there will be equal number of heads and tails? 11 times you're tossing this. There is no way there are equal heads and tails. These two are equal. Answer is 1/2. What is the probability there will be more heads than tails? 1/2. More tails than heads? 1/2. Neither of these two, not possible. You either have more heads or you have more tails. It is impossible to have anything else. Both of these are equally likely 1/2. If you have your fundas in place, you just read this question, just pinch yourself to see that you're dreaming. Answer 1/2 and move on. Wonderful question, because the guys who know their stuff can answer this in about 20 seconds. Some can still answer it after 2.5 minutes, and then the huge bunch will still not be able to answer it. You should be in the group that just belongs in a 1/2 directly, immediately. Go to the next one. In how many ways can we arrange the letters of the word TWO-IIM such that no two vowels are together? I'm going to rush through this. I want to see if we can do 2 more questions. And we've already seen this template. No two vowels should be together. So this is, we're looking at word TWO-IIM. The vowels are O-I-I. The consonants are T-W-M. Put the consonants together, T-W-M. They can be rearranged 3 factorial for 6 ways. Create 4 slots. 1 in between any 2 adjacent consonants. 1 in the beginning, 1 in the end. Out of these 4, select some 3 for vowels. This can be done in 4C3 or 4 ways. Okay. There are 4 ways of selecting the slots. Once you've selected the 3 slots, let's say you've selected these 3, we need to put O-I-I in there. That can be done in 3 factorial by 2 factorial or 3 ways. Or the total number of outcomes is 3 factorial into 4C3 into 3 factorial by 2 factorial, 6 into 4 into 3, whatever that comes out to, 24 into 3, 72 ways. I've seen a question very similar to this. I've done this twice over because this seems to be a more of a standardized template these days. So once you figure out the exact mechanism, you just practically just mechanically identify the answer. Right. We'll go to the next question. See if you can squeeze in a few more. So one battle question or to a tough question. I'm probably going to take the opportunity to flip out of screen share, see what's there on the YouTube screen, and then come back to this. And it will take a little bit of time to solve this question. Take your time, give it a go, we will continue discussing this. Try this question with trial and error approach. Just see what you can plug in, whether you can put in some values and see how this is going. Whether you can substitute some x equal to 6 or 10 or 100 or 1000 or -50, and get a pattern to that. And then see if you can drill down in the pattern and then find something like that. So try that. It's a good question. I'm going to give about probably a minute or 2 more, and then we come back to discussing this. I'm going to flip into screen share mode. This is enough of the annoying teacher that you have seen. So I'm going to go back here and then see how we can work this question. X minus 2 into x minus 4 into x minus 6 into x minus 8 all the way to x minus 100. Straight away you can take it for granted that there's no algebraic way of doing this. We're not going to find an x power large number equation and then factorize it and solve it and all kinds of stuff. That is ruled out. And think of what you're doing here. The best way to go about these questions, especially when the condition says integer values x can take. Plug in a few integer values. put in a few values. Let's say we put x equal to 1000, or we put x equal to 0. And we put a large number, a small number, plug in a 0 because it's one of a beautiful number, India's contribution to the world contribution. See whether 1000 works, see if there's 0 works. Put x equal to 1000 here, 1000 minus 2, 1000 minus 4, 1000 minus 6 on that. Don't multiply, of course don't multiply. Is that going to be negative? That's a question here. 1000 minus 100 is also positive. All terms are positive. We are multiplying n positive numbers. So obviously the product cannot be negative. So this doesn't work. Immediately, straight away, we know that more than 101, nothing will work. From 101 upwards, nothing will work. If you put x equal to 101 or higher, every single term is positive. N terms, all of them are positive. How are you going to multiply their negative term? Nothing works. Good. So we eliminated one giant part of the number line. So brilliant. Now let's do that. Put x equal to 0. You put 0 minus 2, 0 minus 4, 0 minus 6, 0 minus 8. This is negative. This is negative. This is negative. This is negative. Every single term is negative. Product of many negative terms. Will it always be negative? Wait a minute. Product of many positive terms will be positive. Many negative terms, God knows, product would still be positive. How do you now figure out whether it's positive or negative? Is there an odd number of terms, product will be negative. An even number of terms, product will be positive. So how many terms are there here? X minus 2 to x minus 100. 50 terms in the sequence. Even number of terms. So the product will be positive. So x equal to 0 and then 1. What else can we extrapolate from here? X is minus 1, minus 2, minus 3, minus 4. Nothing will work. X equal to 1 won't work. So x less than or equal to 1 doesn't work. So then all terms will become negative, product will become positive. Fabulous. So we have narrowed everything down. We're looking at only integers. We're looking at integers from 2 to 100. That's it. So from the giant number line of all integers, we have narrowed it down. Again, if x minus 2, x minus 4, x minus 6, x minus 8, all of these. Obviously, we can put x equal to 2, 4, 6, 8, 10, 100. Then the equation will go to 0. Those won't work either. So what are we left with? What are the possibilities here? We're looking at 3, 5, 7, 9, 11, 13, 15, all the way to 99. Only these many possibilities exist. We've eliminated all numbers more than 100, all numbers less than 2. We've eliminated all even numbers from 2 to 100. These don't work. We're down to a few other possibilities. Let's substitute x equal to 3. X minus 2, 3 minus 2, this will be positive. X minus 4, 3 minus 4 is negative. This is negative. Everything is negative. So when x is 3, there are many negative terms and only one positive term. Now there are 49 negative terms and one positive term. The product now will become negative. So 3 will work. For our first winner, x equal to 3 works. X equal to 5. Put x equal to 5. X minus 2 is positive. X minus 4 is also positive. We have 2 positive terms. From x minus 6 onward, it becomes negative. 48 negative terms. Even number of negative terms. 5. We put x equal to 7. We have 3 positive terms. And 47 negative terms. Odd number of negative terms. Still work. I think you can already sense a pattern. 9 won't work. 11 will work. 13 won't work. 14 will work. So every other odd number will work. So we have 3, 7, 11, 15, 19, 23, etc. Now how many will work? We need to find a way of counting this. This is an arithmetic problem. I don't want to do this algebraically. The steps of 4. This is 3. 3 plus 4. 3 plus 4 into 2. 3 plus 4 into 3. 3 plus 4 into 4. Till 3 plus 4 into, what is the maximum we can account it here? 4 into 25 is 100. 103 won't count. 24. 3 into 4. 3 plus 4 into 24. All the way from 4 into 1 till 4 into 24. 24 numbers plus this one. Or x can take 25 different integer values, and this inequality will go through. So how many integer values can x take? X can take 25 different integer values. Absolutely fabulous question. Probably slightly at the tougher side because you will get the inequalities idea right. You just substitute a few values and get the pattern. Then eliminate all numbers more than 100, all numbers less than 2. Then eliminate even numbers. Then come down to the odd numbers, select alternate odd numbers. So quite a time-consuming process. So it might lose out or it might not come because it will take a while to lose. But otherwise, good question, good practice to think about inequalities in positive terms and negative terms. What about the next question? How many non-empty subsets of set S exist? Set S is set of all elements such that the product of the elements of the subset is an even number. Take about 30 seconds to 45 seconds. Think about this question, give it a go, and then we'll discuss this. How many non-empty subsets of set S exist such that the product of the elements of the subset is an even number? See an example. So we could have an example of set which is 2, 5, 7. 2 into 5 is 7, even number. 3 into 4 into 6. 3 into 4 into 6, even number. So these are all subsets that we will end up counting. Will all get counted. What will not get counted? If you have 1 into 3 into 7, it will not get counted. 1 into 3 into 7 is an odd number. So we should count subset like this. We should not count subset like this. That's what we're looking at. I'm just outlining this question. Very often in these counting questions, selecting one clear selection that will get counted and one clear outline that will not get counted. Very often gives amazing clarity. What's the clarity we've got here? When will something get counted? When will something not get counted? Product of the number should be an even number. Even if there is one even number, the product will become even. So if there's one even number in the set, the product will become even. No even numbers, or if all the numbers are odd, then the product will become even. If you think about this, it's very difficult to count subsets where there's at least one even number. Far simpler to count this. Think about that. Our set S, think about number of subsets of S. This is 2 power 12 minus 1. We're doing a non-empty subsets. That is doable. You should know the formula, you should know why that formula works. Within this S, we're going to now think about elements or subsets that will not get counted. Or we're looking at subsets that have only odd numbers. How do we do that? That means we're looking at 1, 3, 5, 7, 9, 11. Any subset of this set will also be a subset of S. And any subset of this set will have the product of its elements being an odd number. So all we need to think about how many subsets this set has. That's 2 power 6 minus 1. Again, we are eliminating the empty set. So the question says how many non-empty subsets of set S exist. So this many total non-empty subsets exist. This many non-empty subsets exist where the product of the digits is an odd number. The product should be even. 1 power 2 power 12 minus 1. Minus 1 2 power 6 minus 1. That's 2 power 12 minus 2 power 6. 2 power 6 2 power 6 minus 1. 64 into 63. Whatever that answer. Wonderful question. Methodically you can solve. Only idea we need to know is product of any number of odd numbers is an odd number. Product of some numbers, in that list if there's even one even number, the product will become an even number. Nothing more than that. I want to shoot for you to read the last question. Tougher ones. Give it a read. Let's see if we have a time, we'll think about discussing this. I'm going to flip over to the YouTube channel and then come on this. Just at the 11 o'clock mark, so I'm not going to discuss this. We've kept a few questions which are present there. Good questions. So give that question also a go. We'll probably shoot to have one more session on permutation combination before CAT. and do relevant questions. These 12, 13 are good fun questions. We will do more relevant fun questions. We'll probably post some of these really tougher questions, but I don't want to spend a lot of time solving tougher questions. This goes to things. So I had a good time. So many thanks for anyone there. I quite enjoyed myself. Best wishes for that. Every time we connect each session, you guys, we always say we should talk something about the product and all that. Right? So do check out online.com. We built an absolutely outstanding product. Of course, I will say that, but you can check it out. And so we can view about 15 to 20 hours of content for free. So please take the time out and view that content. We have tried to create content whether videos, slides, tests, quizzes, benchmark questions, levels of various level of difficulty. The most important part, which we feel like, is extremely modularized, where you can set your pace. Like this session is a 1-hour session. If this were a class inside your course, it would be 13 questions and 13 answers, and each of them would be a 3-minute, 4-minute video. So if you get a question, I don't want to look at the video. I know this question. I know that if you toss a coin 11 times, more head than tail, tails 1 by 2. What's Rajesh going to say that's too difficult? You skip that question and then go to the next one. So a 1-hour class which is live on YouTube is probably only about half an hour of content for you when you have to go through that inside the course. Right? The same thing works the other way around. So sometimes in 1-hour content, there's one question which is deliciously beautiful, where I thought that the solution was wonderful, but for the life of me, I'm not sure exactly how they went about it. So you can go back and listen to that bit once, twice, thrice, see what is a cross-linked bit of theory there, and then check that out. So therefore, you can relearn a bunch of ideas which you're slightly unclear about, and skip the parts that you're clear about. Do check it out because you put a lot of thought and effort into creating the platform and with quizzes and benchmark tests that we have, so that we can help you set the pace really well. So the website to go for it is online.TWO-IIM.com. So we will most likely have sessions practically every week or every other week from now till Q. So coming Saturday, 10 to 11, we will have a session. Internally, we have not decided what the topic will be. Either be number systems or it will be logical reasoning. One of these two. We've done about 4 sessions on DALR so far online. All those are available on the YouTube channel and inside the course. We want to squeeze in maybe 1 or 2 more. But that apart, we'll look at number system and then we'll move to geometry. Best wishes you can. Put in everything you can in the last 2.5 to 3 months. There'll be gazillion people who tell you there isn't enough time to don't listen to any of them. So back yourself, build in that belief, and have a good go at this exam.